Hello, welcome to section 5.9, where we're going to talk a little bit about chiral molecules that are chiral based on the fact that they cannot uh, twist or flip, meaning that they are conformationally locked in place. And even though they are conformationally locked in place, they are chiral without a chiral carbon. So the first type of example is shown here. Well, that's not shown. The name of those types of compounds is shown here, called atrope isomers. And atrope isomers are molecules locked into a plane into a plane of molecules locked into a single conformation. They can't rotate. Examples of this are shown in your book here. One good type of example yeah. Okay, one good type of example. It's like this, where we have some ring, like let's say it's a very flat ring like this, a double bond, single bond, double bond ring called a benzene here. And then 90 degrees to that, I'm going to try and draw it here. Yeah. A little hard to see. Let's try it one more time. There we go. Another benzene ring there. And it is sort of coming out at us and going in, trying to show that it cannot, or that they're not flat together. So if you put something at these two positions on the benzene ring like this, then it's very difficult for the other benzene ring to rotate around. And in fact, if these two things are big enough, then that benzene ring is said to not rotate at all. And so you can have chiral molecules based on these types of atrope isomers, and you can separate them and get enantiomerically pure materials. Okay, another type of atrope isomer are allenes, and they're a pretty weird type of compound, especially because they have this structure. One of the reasons why they're weird is because they have the structure I'm about to draw here. Remember, R can be anything in organic chemistry. So if you notice, for allenes, they have on one side, on the left side here, these are normal bonds and in the plane of the paper. But on the right side here, these are coming out and into the paper. And what that means is that it's totally 90 degrees from the stuff on the left. And because these are double bonds, these molecules, the R's on the left and right side, can't rotate. And because of that, these are chiral molecules that you can separate into enantiomerically pure, meaning um, single enantiomer compounds. So if we were to make these, oh, I forgot the rest of the R there. If we were to make these R's into something that is not just R, so let's say We delete each R. And we put instead like a CH3 here. There we are. Then what we can do is draw the enantiomer of this allene. So we'll have a carbon with a dash and a wedge. And that's CH3. And that's CH3. And remember, this is conformationally locked, so that means it doesn't have to have 4 groups. It needs to have 2 groups that are different. So this should be, instead of CH3, should be ethyl or something else. Can't be CH3. We'll say it's ethyl. There we are. Okay, so then we can make the confirmation that not only is this a mirror image, but it is non-superimposable, right? Because the stuff on the left is not the same as what was on the left in the mirror image. So these are true enantiomers, and they are non-superimposable mirror images of each other. All right, and that was section 5.9 on chiral compounds that lack a chiral center.